For most of human history, the universe felt large, but it also felt stable. The stars were distant, but they obeyed rules. The sky looked endless, yet it behaved in ways that could be predicted once you learned the language of physics. Even when astronomy became scientific, when myths gave way to equations, there was still comfort in the idea that reality made sense. We believed the universe was coherent. The James Webb Space Telescope was built to reinforce that belief. Not to shock us, not to rewrite everything, but to confirm the story we already thought we understood. Its purpose was simple. Look further back in time than any telescope before it and fill in the earliest chapters of cosmic history with higher resolution. The expectation was not mystery. It was confirmation. And that expectation matters because the early universe was supposed to be quiet. After the Big Bang, there was meant to be a long pause. A stretch of time where nothing dramatic happened. Just hot gas expanding, cooling, thinning out. Gravity working slowly, patiently, doing what gravity always does. Pulling matter together grain by grain over hundreds of millions of years. This delay was essential. Without it, nothing else in the timeline works. Here's why. Gravity is not explosive. It doesn't rush. It gathers. Galaxies are not sudden events. They are construction projects. Clouds of gas collapse. Stars ignite. Those stars live for millions of years, then die, scattering heavier elements into space. Only after that can the next generation form. This cycle has to repeat again and again before you get anything complex. That takes time. So when James Webb began sending back images, the first reaction wasn't awe. It was confusion. Deep in the past, far earlier than anything recognizable should exist, it wasn't seeing faint smudges or tentative beginnings. It was seeing galaxies. Bright ones, massive ones, fully structured systems sitting uncomfortably close to the start of time. And so we have to ask, why is that a problem? Because according to the standard timeline, some of these galaxies appear less than 300 million years after the Big Bang. On human scales, that sounds enormous. On cosmic scales, it is nothing. It is barely enough time for the first stars to turn on, let alone for entire galaxies to grow, mature, and stabilize. There simply isn't enough time for gravity to do that much work. The equations don't flex here. They snap. If gravity behaved differently in the early universe, that difference would echo everywhere. If star formation was radically faster, the universe today would look completely different. But it doesn't. The universe now behaves exactly as predicted, which means the past should have followed the same rules. And yet, the galaxies are there. But size alone is not the real problem. What truly breaks the timeline is what those galaxies are made of. James Webb doesn't just see light. It reads chemistry. By breaking that light into its component wavelengths, it can tell which elements were present inside these ancient systems. This is where things stop being uncomfortable and start being impossible. The Big Bang created almost nothing but hydrogen and helium. No carbon, no oxygen, no nitrogen. None of the elements required for planets, chemistry, or life. Those elements must be forged inside stars. A star has to form, burn for millions of years, and then die violently to scatter those ingredients into space. That process cannot be rushed. But when Webb analyzed the light from these early galaxies, it found strong signatures of heavy elements. Carbon, oxygen, dust. The unmistakable fingerprints of multiple generations of stars already having lived and died. So now we have to stop and ask something much harder. If the universe was only a few 100 million years old at that point, where did all that time come from? Because the chemistry does not lie. Those elements cannot exist without a long stellar history behind them. Entire generations must have already passed. Which means that, somehow, an enormous amount of cosmic time is missing from the story we thought we knew. This is the moment where the discovery changes character. For decades, cosmology relied on the quiet assumption called the cosmic dark ages. After the Big Bang, the universe was supposed to be dark for hundreds of millions of years. No stars, no galaxies, just expanding gas and silence. Only later did gravity slowly pull matter together and switch the lights on. James Webb erased that darkness. The data shows light everywhere, far earlier than predicted. Not isolated sparks, but sprawling regions of star formation. The dark ages were not dark at all. The universe did not wake up gradually. It was active almost immediately. And now we have to ask why that matters. It matters because the entire structure of modern cosmology depends on delay. Dark matter was supposed to build an invisible framework first, with ordinary matter settling into it later. That framework takes time to assemble. But the galaxy's web is seeing look like they skipped the waiting period entirely. Normal matter organized itself with shocking speed, as if the universe already knew where everything was meant to go. At this point, there are only two options. Either the measurements are wrong, or the story is. The measurements come from one of the most carefully engineered instruments ever built, operating exactly as designed. The same results appear again and again across independent observations. The telescope is not hallucinating, so attention turns to the timeline itself. Some physicists have suggested that the universe may be far older than we think. If cosmic time has been misread, if the expansion history has been misunderstood, then perhaps there was enough time after all for these galaxies to form. An older universe would ease the tension. But here's the catch. Fixing the timeline breaks everything else. Expansion rates, dark energy models, background radiation. Saving one piece of the story means destabilizing the rest. Other ideas are even more unsettling. Some suggest the Big Bang was not a beginning at all, but a transition. That the universe inherited structure from something before it. Not creation, but recycling. A previous cosmic phase collapsing and resetting, leaving behind traces we are only now seeing. These ideas were once fringe. James Webb forced them back into the conversation by making the standard explanation harder to defend. And now the problem shifts again, away from time and toward space. Because as the universe grows larger in our view, it also becomes more confined. There is a physical boundary to what we can ever observe. A horizon formed by the speed of light and the expansion of space. Beyond it, information can never reach us. Galaxies near that edge are already disappearing, carried away faster than their light can travel back. Every moment, parts of the universe fall out of reach forever. James Webb was designed to stare directly at that boundary. And what it finds there is not emptiness. It finds complexity pressed right up against the limits of visibility, as if the universe does not thin out with distance, but simply vanishes. This is where scale starts to feel different. Not open and infinite, but sealed. A bubble of reality surrounded by permanent darkness. A universe that is not just vast, but isolating by design. And this is only the beginning of the problem. Once the timeline begins to fracture, the instinct is to stop looking backward and start looking outward. If the early universe behaved strangely, perhaps the large-scale universe we live inside now is calmer. After all, even if the beginning was chaotic, Surely the structure that has had billions of years to settle should now be stable? That assumption feels reasonable. Old systems tend to quiet down. Mature structures drift toward equilibrium. A universe this old should look relaxed. But this is where the discomfort deepens. When astronomers map the motion of galaxies across the sky, they expect randomness. On the largest scales, individual clusters should drift in different directions, each responding to local gravity. That randomness is not noise, it is the signature of balance. It is what a settled universe looks like. Instead, something else appears. Large groups of galaxies are moving together. Not subtly, not locally. Entire clusters are flowing in the same direction across vast distances, as if caught in a shared current. And now we have to ask, why would that happen? Gravity alone cannot explain it. There is not enough visible mass pulling them. Dark matter does not fix the problem either. Even when every known contribution is added up, the motion remains too coherent, too aligned, too fast. The equations refuse to close. This phenomenon is often described as large-scale bulk flow, but the name hides how strange it actually is. Imagine a city where every building, every street, every river is slowly sliding in the same direction. Nothing is collapsing. Nothing is shaking. Everything is just moving. Together, with no visible cause. That is what the universe appears to be doing. So we have to pause and ask, if matter is flowing, what is shaping the flow? Either the universe is not as uniform as assumed, or there is structure beyond what we can see. And here, the boundary problem returns. Because if the source of this motion lies outside the observable universe, then something unseen is influencing everything inside it. At this point, space stops feeling empty and starts feeling crowded. The tension sharpens when expansion enters the picture. For nearly a century, cosmology relied on a simple expectation. Measure how fast galaxies are moving away and infer how the universe evolves. This expansion rate should be a single number, one value. Measurable in different ways, but ultimately the same. It is not. There are two independent ways to measure how fast the universe is expanding. One looks far back, to the earliest light in existence. The other looks nearby, at stars and galaxies close enough to measure directly. Both methods are precise. Both are reliable. And they disagree. So now we have to ask, how can the universe disagree with itself? The early universe predicts a slower expansion. The local universe shows a faster one. The gap is not small. It persists across instruments, surveys, and corrections. James Webb did not soften this discrepancy. It hardened it. This conflict has a name, but the name understates the issue. It is not just tension. It is inconsistency. The present is expanding in a way that does not line up with the past. And that raises an uncomfortable question. Has the universe changed its behavior over time? If so, something fundamental is missing from the model. Either an unknown form of energy acted briefly and vanished, leaving only subtle fingerprints behind, or the laws governing expansion are incomplete. Neither option is reassuring. If an unknown energy existed early on, then it shaped everything we see today and left almost no trace. If the laws themselves are incomplete, then our predictions about the future are built on unstable ground. And this is where scale begins to feel threatening rather than impressive. Because expansion is not merely happening, it is accelerating. Space is not just stretching, it is stretching faster over time. Distant galaxies are not only moving away, they are crossing a threshold beyond which they can never be reached or even observed again. So we have to ask, what does that do to our place in the universe? The universe is getting larger, yet our accessible portion is effectively shrinking. The cosmic horizon tightens, not because space is collapsing, but because it is expanding too quickly. We are surrounded by distance that cannot be crossed. James Webb was built to look directly toward that horizon. And the closer it looks, the less simple the edge becomes. Instead of smooth uniformity, it finds structure. Instead of fading complexity, it finds organized matter pressed up against the limits of visibility. Which forces the next question. If the universe is accelerating, and if its expansion history does not agree with itself, what happens if that acceleration does not stabilize? In extreme scenarios, expansion eventually overwhelms gravity, then atomic bonds, then even the forces holding matter together. Structures unravel. Not explosively, but inevitably. Galaxies disperse. Stars lose their planets. Matter itself begins to fail. This is not an explosion. It is unbinding. And the unsettling part is not that this might happen far in the future. It is that the underlying behavior is already visible. The disagreement in expansion rates suggests the universe is not coasting toward a known outcome. It is drifting into unfamiliar territory. Once again, the problem is not size. It is predictability. A universe that behaves consistently can be navigated. A universe that quietly changes its rules cannot. The James Webb data does not show chaos. It shows order that does not match expectation. Motion without sufficient cause. Expansion without agreement. And that brings us to the most uncomfortable question yet. If space itself is behaving in ways we do not fully understand, is the emptiness between galaxies really empty at all? Once doubt enters the vacuum, it does not stay contained. If space itself may be active rather than inert, then the question shifts from motion and expansion to stability. A universe can be strange and still be safe. It can behave unexpectedly and still be solid underneath. So now we have to ask, is the foundation of reality actually stable? For most of modern physics, empty space was treated as the lowest possible state. Remove all matter, remove all radiation, and what remains is nothing. A quiet baseline. A floor beneath existence. But quantum mechanics never allowed that simplicity. Even a perfect vacuum seethes. Fields fluctuate. Energy appears and disappears. The emptiness is restless. That restlessness raises a disturbing possibility. What if the vacuum we inhabit is not the true bottom? What if it only appears stable because it is stuck on a ledge? This idea is known as false vacuum decay, and it sounds abstract until its implications are made concrete. Imagine standing on a wide frozen lake. The ice feels solid. You can walk across it. You can build on it. But beneath the ice is deep water. You are not standing on the ground. You are standing on a surface that only feels permanent. Now we have to ask, how would we know if we were standing on ice? The answer lies in the properties of the fundamental fields that give particles their mass. Measurements of these fields suggest something unsettling. The values that define our universe sit uncomfortably close to instability. Not clearly safe. Not clearly doomed. Balanced on the edge. This does not mean collapse is imminent. It means collapse is possible. If the vacuum were to decay, it would not do so gradually. It would not announce itself. A tiny region of space would slip into a lower energy state, a truer vacuum. Inside that region, the laws of physics would be different. atoms would not hold together. Chemistry would fail. Matter would lose its structure entirely. And so we have to ask, what happens next? That region would expand. Not slowly, not explosively. It would expand at the speed of light. No signal can outrun it. No warning can arrive before it does. One moment, reality behaves as expected. The next moment, the rules that allow matter to exist are gone. There is no experience of this event, no perception, no pain. The structures that support deception disappear before they can register what is happening. This is not fear meant to shock. It is a logical consequence of how fields behave. The most unsettling part is not that such an event could happen far away. It is that distance offers no protection. A vacuum decay triggered 1 billion light-years away would arrive here without advance notice. The light carrying the image of the disaster and the disaster itself travel at the same speed. So we have to ask, could it already be on its way? There is no answer to that question. And that absence of an answer is the problem. A stable universe allows prediction. An unstable one does not. At this point, the ground beneath cosmology begins to feel thin. Time does not behave as expected. Space does not behave as expected. Expansion does not agree with itself. And now, even emptiness may be temporary. So attention turns to the one place where physics has already broken completely. Black holes. They are the only objects in the universe where gravity overwhelms every other force. Matter falls inward and never returns. Light itself cannot escape. For a long time, black holes were treated as cosmic trash cans. Things went in. Information disappeared. End of story. But that story turned out to be wrong. The amount of information a black hole can contain does not depend on its volume. It depends on its surface area. This realization alone reshaped physics. It means that when matter falls into a black hole, the information describing that matter is not stored inside. It is encoded on the boundary, on the event horizon itself. And now we have to stop and think about what that actually means. If information does not live in volume, then volume may not be fundamental. If everything that falls into a black hole is recorded on a two-dimensional surface, then the third dimension we experience might be an illusion. This is not metaphor. It is math. The implication is that reality may behave like a hologram, a three-dimensional experience emerging from information written on a distant surface. Depth, solidity, and separation are effects, not fundamentals. And so we have to ask, if this applies to black holes, why would the rest of the universe be exempt? The observable universe also has a boundary, a horizon defined by light and expansion. If information is encoded on horizons, then the information describing everything we see may be stored there as well. That means space is not a container. It is a projection. The unsettling part is not philosophical. It is practical. A projection can glitch. It can blur. It can fail at the edges. James Webb is looking deeper and deeper toward that cosmic boundary. And the closer it looks, the more anomalies appear. Structures forming too early. Expansion behaving inconsistently. Motion without clear cause. So now we have to ask, are these problems with physics, or are they limits of resolution? If reality has a smallest unit, a minimum scale below which it cannot be divided, then the universe has pixels. At those scales, smooth motion breaks down. Continuity becomes an illusion created by rapid jumps between discrete points. And if the universe has resolution, it must have limits. This does not require simulation language to be unsettling. Any system with finite resolution can fail when pushed too far. Errors appear. Assumptions break. Unexpected artifacts emerge. The deeper James Webb looks, the closer it gets to the edge of what the universe can render cleanly. Which raises a final question for this section. If the structure of reality itself is under strain, if time, space, expansion, and emptiness all show signs of instability, then what exactly are we standing on? And is it as solid as it feels? Once the stability of space itself is in question, it becomes impossible to ignore another silence that has lingered for decades. Not a silence in equations or measurements, but a silence in the sky. A quiet that grows louder the more powerful our instruments become. Because if the universe is this old, this large, and this active, then it should not be empty of life. For a long time, that assumption felt safe. Life arose here, so why not elsewhere? The galaxy contains hundreds of billions of stars. Many of them host planets. A significant fraction sit in regions where liquid water could exist. On paper, the odds appear generous. So we have to ask, where is everyone? This question is not philosophical. It is statistical. If intelligent life were common, even moderately so, the galaxy should show signs of it. Not necessarily visitors or messages, but footprints, energy use, waste heat, chemical imbalance, something that breaks the natural equilibrium of dead matter. For decades, the search focused on radio waves. We listened. We assumed that advanced civilizations would announce themselves, broadcasting into the void. But this assumption quietly carried human psychology with it. It assumed curiosity over caution, visibility over survival. And now we have to ask, was that assumption ever reasonable? In nature, being loud is rarely an advantage. Visibility attracts attention. Attention attracts risk. If survival is the goal, silence is often the better strategy. A civilization that lasts learns this quickly. The James Webb Space Telescope marks a shift in how the search is conducted. Instead of listening, it observes. Instead of waiting for messages, it examines atmospheres. Because technology can be hidden, biology cannot. Life is chemistry pushed out of balance. It consumes energy and produces waste. It alters the air around it in ways that cannot be easily disguised. Oxygen, methane, ozone, industrial pollutants. These are not neutral signatures. They are flags. So we have to ask, what happens when we start looking for those flags? James Webb has already begun scanning the atmospheres of distant worlds as their stars shine through them. During these brief transits, starlight passes through alien skies, carrying with it a chemical fingerprint. Certain wavelengths are absorbed. Others pass through. The result is a spectrum that reveals what is floating in that air. This is not speculation. It is measurement. And what the measurements show is unsettling. Many of the worlds examined so far have atmospheres that are chemically stable, calm, dominated by a single gas or a simple mixture that has settled into equilibrium. Carbon dioxide without oxygen, nitrogen without reactive companions. No tension, no ongoing activity. And so we have to ask, what does stability mean in this context? In chemistry, stability is death. Reactive mixtures do not last unless something is constantly replenishing them. On Earth, oxygen and methane coexist only because life continuously produces both. Without biology, they would react and vanish. A stable atmosphere is an exhausted one. The pattern that emerges is not of a galaxy teeming with life, but of a galaxy dominated by stillness. Worlds that appear to have finished whatever story they were going to tell long ago. Or worlds where the story never began. This leads to an uncomfortable possibility. Perhaps life is not easy. Perhaps it is not the natural outcome of water and sunlight. Perhaps it is a rare event, requiring an improbable alignment of conditions that almost never occur together. So now we have to ask, how fragile is the path that led here? The requirements begin to stack up quickly. A stable star that does not erupt violently. A planet with a magnetic field to shield its surface. A large moon to stabilize its rotation. Gas giants positioned to intercept catastrophic impacts. Plate tectonics to recycle nutrients. A climate that remains within narrow bounds for billions of years. Remove any one of these, and the chain breaks. James Webb does not show us a galaxy full of gentle suns and quiet systems. It shows violent stars, chaotic orbits, planets stripped of their atmospheres, systems that never settle. The implication is not comforting. If life requires this many constraints, then the universe may not be waiting to bloom. It may be hostile by default. Life might not spread naturally. It might flicker briefly and disappear, which forces a darker question. If life is rare, what about intelligence? Intelligence is not just biology. It is biology that has survived long enough to reflect on itself. It is chemistry that learned to manipulate energy deliberately. That step introduces a new kind of risk. Technology accelerates faster than wisdom. Power increases faster than restraint. The ability to destroy often arrives before the ability to understand consequences. So we have to ask, if intelligent life emerges elsewhere, how long does it last? The silence of the universe may not indicate absence. It may indicate brevity. Civilizations may appear, burn brightly, and extinguish themselves before leaving a detectable mark. A short technological window produces very little cosmic noise. In that case, the sky is not empty. It is quiet for the same reason a battlefield falls silent after the fighting ends. And this leads directly to a more unsettling framework. If survival is uncertain, and if visibility increases risk, then silence becomes strategy. The universe may not be empty. It may be watching, not waiting to greet, waiting to avoid being seen, which reframes the silence entirely, not as loneliness, but as tension. And if that is true, then the next question is unavoidable. If silence is survival, what does that say about a species that has spent the last century broadcasting its presence into space? If silence is not emptiness but strategy, then the meaning of the quiet sky changes completely. It stops being a mystery to solve and becomes a behavior to interpret. The absence of noise is no longer neutral. It is information. And once we accept that, the universe begins to look less like an unexplored wilderness and more like a place where things are deliberately keeping their distance. At that point, we have to reconsider one of the most comfortable assumptions we have ever made, the belief that intelligence naturally spreads outward once it appears. That belief feels intuitive because it mirrors our own history. We invent tools. We invent machines. We push outward. We explore. But intuition is not evidence, and the James Webb data keeps forcing us to abandon what feels natural in favor of what is consistent. To understand why silence might be the default state of an intelligent universe, it helps to strip the problem down to pure logic. Imagine two distant civilizations, separated by thousands of light years. Neither knows anything meaningful about the other. No culture, no ethics, no intentions. All that is known is that the other exists, and that it has access to technology powerful enough to cross interstellar distances, or at the very least to manipulate energy, on planetary scales. Now ask what information can be trusted. Friendly signals could be genuine or deceptive. Silence could be fear or patience. Delay destroys certainty. Even if a message is received, it describes a sender who no longer exists in the same state. Decisions must be made in the dark, with incomplete data and irreversible consequences. In that environment, caution is not paranoia, it is rational. This is where the idea of a cosmic dark forest emerges, not as a metaphor, but as a logical outcome of uncertainty. In a dark forest, every rustle could be prey or predator. Visibility increases vulnerability. Revealing position removes options. And because distance prevents verification, trust becomes impossible to establish. The safest assumption is that anything capable of harming you eventually will, whether intentionally or accidentally. From that perspective, survival favors civilizations that minimize their footprint, mask their emissions, and avoid drawing attention to themselves. Loud civilizations do not persist long enough to become common. Quiet ones do. Once this logic is taken seriously, the absence of obvious technological signatures stops being surprising. It becomes expected. We should not expect a sky full of beacons, messages, or megastructures. We should expect carefully managed energy use, waste heat disguised as natural processes, and communication kept tightly localized. The universe would appear calm, orderly, and lifeless, not because nothing is there, but because anything that remains has learned to blend in. Stability once again becomes a warning sign rather than a comfort. This reframing casts human behavior in an uncomfortable light. For roughly a century, Earth has been leaking information into space. Radio broadcasts, radar pulses, television carriers. Signals that expand outward at the speed of light, announcing not just our presence, but our technological immaturity. These signals encode our biology, our culture, our location, and our developmental stage. They reveal a civilization that has learned how to manipulate energy, but not yet how to restrain itself. In the logic of the dark forest, this is not curiosity. It is recklessness. The unsettling part is not that this guarantees danger. It is that it removes ignorance as a shield. Any civilization within range now knows that a young technological species exists here, confined to a single planet, broadcasting loudly and possessing a biosphere rich in resources. Whether that knowledge leads to action is unknowable. But the moment the information exists, the strategic landscape changes permanently. Silence can no longer protect what has already been revealed. At this point, it is tempting to retreat into reassurance, to argue that distances are too vast, travel too slow, or intentions too benign for concern. But those comforts depend on assumptions that the rest of the data does not support. We already know that physics allows for energy delivery without physical presence. We already know that simple objects, accelerated to extreme speeds, carry catastrophic force. We already know that time delays erase warning. A decision made far away could be unfolding toward us right now, invisible by the very laws that govern causality. This is where the scale revealed by James Webb becomes oppressive rather than inspiring. A larger universe does not dilute risk. It multiplies it. More stars mean more potential observers. More time means more opportunities for asymmetry to emerge. More distance means less chance of correction once a course is set. The same vastness that makes the universe feel majestic also makes it unforgiving. Yet even this does not represent the deepest threat implied by the data. Because external dangers are still dangers that come from outside. They preserve a boundary between observer and environment. What James Webb truly destabilizes is that boundary itself. The telescope does not just show us what exists elsewhere. It reveals that the structure of the universe may not be as passive as assumed. Expansion accelerates unpredictably. Large-scale motion resists explanation. Vacuum stability becomes uncertain. Information behaves in ways that undermine our intuition about space and depth. These are not background conditions. They are properties of the stage we are standing on. If the universe were merely dangerous, that would be one thing. Danger can sometimes be navigated. What the data increasingly suggests is that the universe may be indifferent to coherence itself. Laws hold until they do not. Structures persist until they fail. Predictability erodes quietly, not with catastrophe, but with discrepancy. The terror here is subtle. It is the realization that the ground rules might not be permanent. And this returns us to the question that has been hovering beneath everything since the first impossible galaxies appeared. What does it mean to exist in a universe that does not seem designed to preserve complexity? Life, intelligence, culture, memory, all represent localized resistance to entropy. They are fragile patterns held together by constant effort. If the broader universe trends toward erasure, then the survival of those patterns is not guaranteed by scale or age. It is contingent, temporary, and vulnerable. The James Webb Space Telescope did not reveal this by intention. It was not built to unsettle. It was built to clarify. But clarity has consequences. By extending our vision, it has stripped away assumptions that once provided comfort. The universe is not simply larger than we thought. It is harsher, quieter, faster, and less stable. And within that environment, persistence itself begins to look like an anomaly, which leaves one final, unavoidable tension hanging in the air. If complexity is rare, if silence is strategy, if stability is uncertain, then survival is not something that happens automatically. It is something that must be actively maintained. And that realization forces the question inward rather than outward. In a universe like this, what does it actually mean to last? If lasting is not automatic, then survival stops being a background assumption and becomes an active problem. Not a moral one, not a philosophical one, but a physical one. Patterns do not persist simply because they exist. They persist because conditions allow them to. And the James Webb data increasingly suggests that those conditions are narrow, temporary, and easily disrupted. The universe does not appear to reward longevity. It appears to tolerate it briefly. At this point, it becomes necessary to confront an uncomfortable inversion. For a long time, intelligence was treated as an advantage, the natural endpoint of evolution. Bigger brains meant better tools, better prediction, better survival. But when intelligence is placed inside a universe that scales this violently, that assumption begins to wobble. Intelligence does not just allow understanding. It enables acceleration. It shortens feedback loops. It concentrates power. And those effects can become liabilities as easily as they become assets. This is where the idea of a universal filter emerges, not as speculation, but as a statistical inference. When something is easy to start but rare to observe, it suggests that it fails somewhere along the way. If simple life is common but advanced civilizations are not, then the barrier is not at the beginning. It is later. Somewhere between emergence and endurance, something repeatedly goes wrong. And so we have to ask, where does failure most likely occur? The James Webb observations do not answer that directly, but they narrow the possibilities. They show environments that are volatile, stars that flare violently, systems that destabilize quickly, worlds that lose their atmospheres. Add intelligence to that mix, and the fragility compounds. A species that learns to manipulate energy gains leverage over its environment faster than it gains restraint over itself. The timeline between discovery and misuse shrinks as technology accelerates. Power scales exponentially. Wisdom does not. This creates a dangerous compression of risk. A civilization may spend billions of years as harmless biology, then only centuries as a technological actor. In that brief window, it acquires the ability to alter its planet, weaponize physics, and destabilize its own conditions for survival. The silence of the universe could be explained by this imbalance alone. Most civilizations may not fail because they are attacked, but because they overshoot. What makes this particularly unsettling is how closely it mirrors what is already visible. Planetary climate altered in a geological instant. Energy consumption rising faster than adaptation. Systems optimized for growth rather than stability. These are not alien patterns. They are familiar ones. And in a universe that does not provide margins for error, familiarity is not comforting. At the same time, external pressures do not disappear simply because internal ones exist. A civilization struggling to manage its own growth does not exist in isolation. It exists within a larger environment governed by forces it cannot negotiate with. Expansion accelerates. Horizons close. Radiation accumulates. The background conditions evolve regardless of intention. Survival becomes a race against both internal collapse and external change. This is where the sense of scale turns inward again. A larger universe does not grant safety through abundance. It imposes pressure through exposure. The more there is to react to. The more time passes, the more opportunities arise for instability to manifest. Endurance in such a system is not a default outcome. It is a narrow corridor. The James Webb Telescope forces this realization not by exaggeration, but by precision. It shows that complexity appears early, but does not necessarily last. It shows that structure forms quickly, but stability is not guaranteed. It shows that the universe does not slowly shepherd systems toward equilibrium in a gentle way. It allows them to arise, then leaves them to contend with forces that do not care whether they persist. And so the idea of progress quietly dissolves. There is no cosmic narrative pushing intelligence outward and upward. There is no guarantee that what appears will remain. The universe does not appear to have a memory. It does not preserve what has happened. It only enforces what is currently allowed. This reframes existence itself. Life is not a natural climax. Intelligence is not an inevitable triumph. Both are transient states, permitted briefly under specific conditions. When those conditions shift, the pattern collapses. Nothing about the scale of the universe suggests otherwise, which leads to a conclusion that is difficult to sit with. If complexity is temporary and silence is adaptive, then the measure of success is not expansion or visibility. It is restraint. Longevity may belong not to the fastest or the loudest, but to whatever learns to remain balanced within narrowing limits. The James Webb data does not tell us how to do that. It only makes clear that the alternative is disappearance. And once that is understood, the universe no longer feels like a place waiting to be explored. It feels like a system that must be navigated carefully, quietly, and without illusion. Once restraint becomes the metric, everything familiar begins to invert. Growth, which once felt synonymous with success, starts to resemble exposure. Visibility, which once implied progress, begins to look like vulnerability. Even curiosity takes on a different tone. In a universe that does not preserve complexity by default, every additional interaction carries cost. Every signal sent outward is energy spent and information surrendered. Every expansion creates more surface area for disruption. And so the question quietly shifts again, away from how far something can go and toward how long it can remain intact. This is where the James Webb discoveries force an uncomfortable comparison between scale and fragility. On one hand, the universe builds astonishing structures almost immediately. Galaxies appear early, massive, chemically mature, as if the cosmos is exceptionally good at generating complexity. On the other hand, nothing in the data suggests that this complexity is protected. Early formation does not imply endurance. Rapid construction does not imply long-term stability. The universe seems eager to create structure and equally indifferent to whether that structure survives. And that indifference matters, because it means there is no external safeguard, no cosmic buffer that steps in when systems approach collapse. Stars exhaust their fuel. Galaxies quench their star formation. Entropy advances without preference. When conditions change, complexity does not negotiate. It dissolves. This pattern appears again and again. Young galaxies burn brightly and then fade. Star formation spikes and then shuts down. Worlds lose their atmospheres. Systems destabilize. What remains is not flourishing, but residue. The James Webb Telescope is effectively giving us a time-lapse of this process across billions of years, and the trend is consistent. Creation is easy. Preservation is not. So now we have to ask, why does anything last at all? The answer seems to be that endurance is not about dominance. It is about balance. Structures that persist do so by staying within narrow operating ranges. Too much energy destabilizes them. Too little starves them. Too much interaction disrupts them. Too little prevents renewal. Survival exists in a corridor, and that corridor appears thinner the larger the scale becomes. This is why the accelerating expansion of the universe is so unsettling. It is not just carrying galaxies away from each other. It is tightening that corridor. Horizons close. Accessible matter decreases. Energy becomes harder to gather. Over time, the universe does not open outward. It thins. What remains connected becomes isolated. What remains isolated cools and fades. In this context, the silence of the cosmos begins to feel less like absence and more like attrition. The universe may once have been loud with activity, with overlapping windows of emergence and collapse. But as time advances, those windows narrow. Fewer systems meet the conditions required to sustain complexity. The quiet is not the starting point. It is the end state. James Webb is not showing us a universe full of unrealized potential. It is showing us a universe in the process of closing its doors. That realization casts a long shadow over the idea of destiny. There is no sense in the data that intelligence is meant to spread, colonize, or endure indefinitely. There is no upward trajectory written into the background radiation or the large-scale structure. What exists does so briefly, under favorable conditions, before those conditions drift out of alignment. And this is where the emotional weight of scale finally settles. The terror is not that the universe is hostile. Hostility implies intent. The terror is that it is neutral in a way that erodes everything slowly, without malice or warning. It allows complexity to arise just long enough for it to recognize its own vulnerability. This creates a strange asymmetry. Awareness arrives late. Understanding comes after the window has already begun to close. A civilization may only realize the nature of the system once it has already committed itself to paths that are difficult to reverse. Growth locked in, infrastructure built, dependencies formed, momentum established. At that point, restraint is no longer simple. It requires deliberate effort against internal pressures that evolved under very different conditions. The same intelligence that enables understanding also enables excess. The same tools that allow survival also enable collapse. Nothing in the structure of the universe resolves that tension for us. The James Webb Space Telescope does not moralize this situation. It does not warn or instruct. It simply reveals the environment as it is. A place where complexity flashes into existence early, burns brightly, and then fades. A place where silence grows with time, not because nothing happens, but because fewer things can continue happening for long. And so, the final shift occurs. The question is no longer whether the universe is large enough to hold life or old enough to generate intelligence. The data suggests it is. The question is whether it is stable enough to keep either around. That question does not point outward toward the stars. It points inward, toward how fragile persistence really is. And that is where the scale of the universe stops being abstract and starts becoming personal. Once the scale of the universe becomes personal, there is nowhere left to retreat. The comfort that once came from distance dissolves. The stars are no longer safely remote. The future is no longer abstract. What remains is the recognition that existence itself is conditional, and that those conditions are not designed to favor permanence. The universe is not hostile in the way predators are hostile. It is hostile in the way erosion is hostile. Slowly, impartially, inevitably. At this point, the question of meaning begins to change shape. For most of human history, meaning was something projected outward. Purpose was assumed to be written into the structure of the world, into gods, destinies, cosmic narratives that moved steadily toward resolution. But the picture revealed by James Webb does not support that framework. There is no evidence of a story unfolding toward a goal. There is only process. Formation followed by dissipation. Complexity followed by simplification. Patterns arising briefly before being erased. And so we have to confront a deeply uncomfortable idea. If the universe does not preserve meaning, then meaning cannot be something we discover. It must be something we generate locally, temporarily, without expectation of permanence. That does not make it false. It makes it fragile. This is where the terror often peaks, because fragility is usually equated with futility. If something does not last forever, we instinctively treat it as lesser. But the universe does not reward endurance. It does not preserve even stars. Permanence is not the metric by which reality operates. Change is. Seen from that perspective, the brief existence of complexity becomes more remarkable, not less. In a cosmos that trends toward equilibrium, every organized structure is an act of resistance. Every living system is a temporary reversal of entropy. Not because it is destined to win, but because it exists at all. The James Webb Telescope shows us that the universe produces these reversals readily, but does not protect them. It allows galaxies to form early, brilliantly, and then leaves them to fade. It allows stars to ignite and burn, then collapse. It allows life, perhaps rarely, to arise under narrow conditions. But it does not intervene to save what it creates. Creation is abundant. Preservation is not. This reframes what survival actually means. Survival is not expansion. It is not domination. It is not visibility. It is coherence maintained for as long as conditions allow. It is balance sustained against pressure. It is restraint in a system that rewards excess briefly and punishes it permanently. If there is a lesson embedded in the scale James Webb reveals, it is not one of insignificance. It is one of responsibility. Not cosmic responsibility, not destiny, but local responsibility. In a universe that does not care, the only thing that can care is what briefly exists within it. That does not grant immunity. It does not promise success. But it does clarify the stakes. The silence of the universe no longer reads as emptiness. It reads as what remains after countless attempts at persistence have already failed. Not because they were weak, but because the conditions that allowed them eventually vanished. The quiet sky is not a promise of safety. It is a record of attrition. And yet, within that attrition, something extraordinary persists. For a brief interval, in a narrow corridor of cosmic history, matter becomes aware of itself. The universe, which otherwise unfolds blindly, produces a system capable of noticing the unfolding. That awareness does not alter the outcome, but it changes the experience of existing within it. The James Webb Space Telescope is an extension of that awareness. It is the universe looking at itself with unprecedented clarity. And what it sees is not comfort. It sees scale without shelter, time without guarantees, complexity without protection. But it also sees that within those constraints, structure still arises, questions still fall, understanding still deepens. Even knowing the outcome does not erase the experience of the process. In the end, the terror is not that the universe is vast, or old, or unstable. The terror is that it does not need us, and never did. And the strange, quiet relief comes from the same realization. If the universe does not assign purpose, then nothing is being taken away. There was no promise to break. What remains is choice. Not cosmic choice, but immediate choice. How complexity behaves during the brief window it is allowed to exist. Whether it burns itself out quickly or holds together carefully. Whether it mistakes scale for safety or understands fragility as a constraint. The universe revealed by James Webb is not a place that guarantees survival. It is a place that permits it briefly. That permission is rare. And that rarity is what gives existence its weight. Not because it lasts, but because, against all odds, it happens at all.